Okay, so just a few announcements before we start the class. Ryan's going to be having a midterm review session tomorrow from 5 to 7. The room is still undecided, or as Jeff said, it's in a quantum state of uncertainty. And once the network's back, we'll send out an email and get the room details finalized. But tomorrow, 5 to 7. Also, I think there was an email sent out regarding the midterm reports. You can use late days for the project midterm report because of Sandy, and that's fine. I think on the website it earlier said that you couldn't use any late days for projects, but we're allowing it. It's fine. Yeah, midterm is November 6th. That's 1 week from today, and not November 8th. It's November 6th. So
yeah, it's Newell Simon 1507 for his
tomorrow. Okay, so tomorrow it's Newell Simon 1507.
Which is the same one that I had.
It's the same one that Jeff had his review session in. So 5 to 7 p.m. tomorrow in NSH 1507. Let me write that for people who might come late. Now I see why Ryan struggles with that. Okay. I mean, it's going out of it. Okay. Okay. I guess we'll start. Yeah, okay. So I'm going to take off from where Ryan left on Thursday. And we were talking about dual methods. And at the end of the lecture, he introduced dual ascent and dual decomposition. I'll start by recapping what we did, just summarize in a few slides what we did. I'll move on to what's called ADMM, which is like a nice combination of the methods at the end of the last lecture, which is the Augmented Lagrangian, along with dual ascent and dual decomposition. And the second half of the lecture will talk about an interesting and slightly advanced algorithm called mirror descent. I'll talk about why I want to introduce this algorithm when we get to it. But let's just say it's one of the exciting algorithms that's out there today. And it's one of the best for high-dimensional problems. So I'll just get started with ADMM. So just to recap what dual ascent was all about, it was for problems of the kind minimize f of x such that ax is equal to b. Okay, so the problem has to be of this kind, and it's an equality over there for the constraints. So we defined a Lagrangian, L of xu, to be f of x plus a dual variable u transpose times ax minus b. As usual, we defined the Lagrange dual function to be g of u, which is just the infimum over x of the Lagrangian, L of xu. And from this, you can just note from the form of the Lagrangian that if I differentiate with respect to u, then what I get is the subdifferential of g at u is nothing but ax minus b. But it's not just any ax minus b, it's ax plus minus b, where x plus minimizes the Lagrange function. So that's the subdifferential of ax minus b. Now the dual problem is to maximize g of u, right? So we just changed the problem from minimizing f of x to maximizing g of u. And so one can think of doing subgradient ascent for g of u to maximize g of u instead of doing gradient descent or something like that on f of x. So that's exactly what dual ascent is. We have the subgradient there. It's just ax plus minus b, where x plus is the minimizer. So let's just go ahead and do dual ascent. And so the algorithm is extremely simple. It just says at every step xt plus 1, I'm going to minimize the Lagrangian of x and the dual variable at the previous time step ut. So I just get the minimizer xt plus 1. And you know that the subgradient is nothing but axt plus 1 minus b. And so I just take a step in the direction of the subgradient, and I'm ascending. So I just add a step size times axt plus 1 minus b. That's also a dual subgradient ascent really is. What do we know about it? For appropriate step sizes, and there are some more technical conditions, we know that xt and ut both, they converge to a primal optimal and a dual optimal point. But if G is not differentiable, this convergence is not necessarily monotone. And what we mean by that is every step need not lead to an improvement. You might have some steps in which G of ut plus 1 is not greater than G of ut. But overall, in the end, it actually does lead to an ascent. It does find you the maximum, and xt and ut will converge to optimal, primal, and dual. Of course, if anyone has questions, just feel free to stop me at any point of time. Just call out in case I don't see you. But yeah, that's dual ascent. It's extremely simple. Just write down the dual function. It's quite easy in this case to find its subgradient. Just do subgradient ascent. That's quite easy. Okay, so this is just a recap of what dual decomposition ascent is. It's called dual decomposition, but I'm calling it dual decomposition ascent because it's basically dual ascent in the special case that the function decomposes. So suppose your function f of x is actually a sum of functions fi of xi, and your xi's are just disjoint subsets of the variables. So you can just decompose your function into the sum of smaller parts. Then what we do is just we write our constraint, which is ax equal to ax minus b of that form, ax equal to b. We write it as the sum over I of ai of xi, right? So I think it should be pretty clear that if I have something of this form ax, I can just write it as just block it out into how many ever blocks there are, and just block the x's out into how many ever blocks there are, and then this is just the sum of ai xi, right? So you can write your constraint as just the sum of ai xi equal to b, and then if you wrote down your Lagrangian, it turns out that the Lagrangian would just decompose over all those functions. So you just have f of x, which is the sum of fi of xi, and you have ax minus b, which decomposes into the sum of ai xi minus like a 1 by n times b. And you have a u transpose there for the dual variable. So if you wrote down your Lagrangian, it would just decompose into smaller parts, right? So then what we have is, if we just wrote down this function and then try to do dual ascent onto a function that decomposes, you'll see that each of the parts in the summation has variables that are independent of all the other parts. And so we can do a dual ascent on each subset of variables independently. So that's all I've written. You just do dual ascent, but here you have xi t plus 1, which is just the subset of variables for the ith block. And we minimize that independently. So you minimize li of xi ut. And so you can do these parallel minimizations and then combine them with the same ascent step for u. So I haven't done anything special. I've just said, okay, this is what dual ascent becomes when your function decomposes into a sum of functions. So this should be pretty straightforward. Yeah, you can keep the. So yeah, if anyone has their reports, they can go ahead and submit it. Okay, so just a short recap of what the augmented Lagrangian was. It's also called the method of multipliers. So the augmented Lagrangian is the first line up there. The usual Lagrangian is just f of x plus a dual variable u transpose ax minus b. And now we augment it with something else. We augment it with this additional term. That's why it's called the augmented Lagrangian. And it just has this squared term at the end over there. So it's rho by 2 times ax minus b the whole 2 norm squared. Right? So that's called the augmented Lagrangian. And we'll see why we might want to do something like that. But it's pretty clear that when ax equal to b, so at primal optimality, when you have ax star equal to b at the optimal, this just reduces to the original problem. So that additional term that you added, rho by 2 times ax minus b the whole square, doesn't really play a role at primal optimality. So you can also think of the augmented Lagrangian as being the normal Lagrangian of a function f of x plus rho by 2 times ax minus b the whole squared, such that ax is equal to b. So if you just wrote the normal Lagrangian of this function f of x plus rho by 2 times ax minus b the whole squared, such that ax equal to b, you just get the augmented Lagrangian. And again, you can see from that at optimality, when ax star is actually equal to b, that additional term that you added doesn't really make a difference, so you're still solving the same problem. So it's basically, it's correct to do this. Now we have to see why it helps us, and we'll come to that. So the associated dual function is, as usual, it's g of u, but there's a subscript rho there because it's the augmented Lagrangian with a penalty parameter rho. And g rho of u is just exactly what it was earlier, just minimize x of the Lagrangian, right? So it's just minimize x L rho of xu. And now what I can do is I can apply dual ascent to this problem, right? So just apply dual ascent, pretty much the same thing again. What you get is xt plus 1, let it be the argmin of L rho of xut. That's the same first step. And the second step, what we're going to do is ut plus 1 is ut plus rho times axt plus 1 minus v. Now just note that the rho is the same thing over there. We don't have a different step size over here. We don't have to choose a different alpha t for a step size. The step size is actually rho, which is the penalty parameter that we used. So if we pick a rho to augment our function, it's the same rho that you do the dual variable step in. And this is pretty clear to see why this is a good step size to take. I think Ryan had it on his slides, but we might have rushed through it, so I'll just sort of recap that in a moment. So what we have is, so I'm just trying to justify why rho is a good step size to take. Let me see if you can see that, right? So we know that xt plus 1, it minimizes L rho of x and ut. Okay, so we know that this is true. So just by by taking subgradients and setting equal to 0, or you'd see that basically if you look at the definition of L rho of xu, I'm just going to take the gradient and set that equal to 0. So at xt plus 1, we have gradient of f of x t plus 1 plus A transpose ut, right? So I've just taken the subgradient of the first two parts, and the last part just looks like, you have a rho times A transpose ax t plus 1 minus b is equal to 0. So since xt plus 1 minimizes L rho, when take the gradient at xt plus 1, that's going to be equal to 0, right? Oops. Okay. Yep. So that's fine. That makes sense. So what does that end up becoming? Just going to write that again. So that's f xt plus 1, right? And if I just take the A transpose term out, what I get is ut plus rho times axt plus 1 minus b is equal to 0. And this is what we defined as ut plus 1, right? So what we get with our update is a nice rule like, we get a nice rule like that, okay, because of the way we chose ut plus 1. Now if you were to write down the KKT conditions at optimality for solving this problem, so the KKT conditions for our augmented Lagrangian, what you'd get is two conditions, of course. One is just primal feasibility. You'd just get that ax star should be equal to b, and you'd get a stationarity condition which looked like gradient of f at x star plus A transpose u star is equal to 0, right? So if I just wrote the stationarity condition down, when I differentiate the last term, you have an ax star minus b remaining, but that's 0. So the last term goes to 0 at the stationary point, and you just get the gradient of f of x at x star plus A transpose u star. So what we can see is that by maintaining the rule gradient of f at xt plus 1 plus A transpose ut plus 1 is equal to 0, by maintaining that rule for xt plus 1 and ut plus 1 at every step, what we see is that if we finally reach a point at which ax star is actually equal to b, we'll be at a point at which it's stationary also, at which gradient of f of x star plus A transpose u star is actually equal to 0, because we're maintaining this invariant condition at every step, and so it'll hold at optimality. So at least this sort of should tell you why we are choosing that particular step size of rho. Makes sense. Okay, and what do we know about this algorithm? We know that it's actually much more robust than dual ascent. By robust, I mean that you don't have all these corner cases that you have to bother about. Like, it converges even if f is not strictly convex, and f can also be, plus infinity at some points. And so that's why we would like to use something like this. But we lost decomposability. So if you note right now that if f of x up there was actually equal to the sum of I f of xi, then I won't be able to decompose that Lagrangian because of that ax minus b the whole squared term. It doesn't decompose into subparts, and so I basically lost decomposability. So this nice property that I had for dual decomposition ascent, that I could solve some problems in parallel and join them, I just kind of destroyed that right now by introducing that augmented Lagrangian there. So what we're going to see now is that ADMM is a kind of method that tries to get you the best of both worlds. It wants to get you this augmented Lagrangian up there to get much more robust convergence properties, and we want to be able to make use of decomposability. That's basically what ADMM is trying to do, right? So it's called the alternating direction method of multipliers. So the previous slide, this is just called the method of multipliers. So if someone told you I'm using the method of multipliers, it's basically this. It's using the augmented Lagrangian, doing this kind of a thing. So this is alternating direction method of multipliers. Okay, yeah, so we're going to pick up the project milestones now. If anyone has a milestone left to submit, it would be a good time. Yeah. Yeah, I'll come back to that. But okay, I guess we're kind of done. And Seth seems unhappy. No, okay. Okay. Why is it called method of multipliers? That's I don't know, Jeff. Why is it called method of multipliers?
Well,
you use a multiplier.
yeah.
It's the method of using multipliers. I don't know.
I mean, I think the multiplier is the same as any time you have duality, right? So all of them would be methods of multipliers. This is particularly the alternating direction method of multipliers, because we're going to do some alternating minimization.
Yep. Yeah, go ahead.
So any guidelines of how to choose row?
Yeah, we'll not come to that, but I will mention that choosing row seems to be an important. It's an important problem for sure. I don't think there's any principled way to choose row, and Ryan says that if you run experiments, then it's actually very finicky to how you actually end up choosing row. But yeah, I don't know of any results. At least in Boyd's papers on this, I haven't seen any results on how to really choose row.
But in general, I mean, if you take it large, what's the disadvantage? If it is small, I mean, it doesn't exist, right? So
yeah, exactly. So if you picked it too large, you'd see that what you're trying to minimize, f of x plus rho by 2 times ax minus b the whole squared, you'd pretty much be drowning out the f of x part. So I'd expect your convergence to be a little slow. Like the weight of that ax minus b the whole square is kind of too large, and it's not listening to f of x enough. If it's too small, yeah, it's as good as it not being there, and then you probably won't get such robust convergence, maybe. Yeah.
Worth mentioning that there are adaptive methods for choosing row. There are, I think, 2 principled adaptive methods for choosing row. But the convergence is also for fixed row. So by choosing adaptively, you actually don't know it's going to converge.
Right. So Ryan mentions that there are adaptive ways to choose row, but the convergence properties are for fixed row. So you can choose it adaptively, but then you don't know it converges. Okay. So ADMM. So again, this is I'm just going to talk about the case where it decomposes into 2 parts. Okay, this generalizes, but we're going to look at the augmented Lagrangian for f of x when it's just the sum of 2 parts. So it's f1 of x1 plus f2 of x2, and their x1 and x2 are disjoint. Right. So I'm just going to write the augmented Lagrangian L rho of x1, x2, and u to be that's just the augmented Lagrangian. It's just f1 of x1 plus f2 of x2 plus u transpose times the constraint term plus rho by 2 times the constraint term squared, right? So ax minus b 2 norm squared. So that's just the augmented Lagrangian. If you look at the bottom, if you did method of multipliers on this, what it would really do is jointly minimize the primal variable. So it will find you a point x, which is the minimizer of L rho of x and ut. So it will just find you a joint minimizer, that is x1 t plus 1, x2 t plus 1, but just one x kind of thing. What alternating direction minimization does is that it it chooses to optimize x1 t plus 1 first, keeping x2 and u fixed. Then it optimizes x2 t plus 1, keeping x1 and u fixed, and then it optimizes u, keeping x1 and x2 fixed. Right? So the only difference is really in the optimization over the x. It splits into two parts. This should look like coordinate descent or ascent for those who have seen that before. Basically, you choose a coordinate to move in the direction of, you optimize it for that, and then you move in some other direction. So in general, things like coordinate descent, again, if you've not seen it, we might see it later. They're not guaranteed to converge. Like, especially if your problem is not smooth, then it needn't converge. It can get stuck. But the interesting thing about this is that we will see that it does actually converge, and we'll talk about convergence on the next slide. But just sort of absorb the algorithm. It's not doing anything special really, but it's interesting that what it's doing, which is so simple, is it actually works. Just splits the variables into two parts, optimize one, fixing the others, and so that it's called alternating direction because of this fix x1 and then fix x2 and optimize the other, that kind of thing. Any questions? Yeah.
Given x2 and u, how do you solve x1? How do you
Given x2 and u, how do you solve for x1? So if you look at the augmented Lagrangian, it's, if you fix x2 and u, then as a function of x1, it looks like f1 of x1 plus u transpose a1 of a1 x1 plus rho by 2 times a1 x1 plus some constant. And so you can just optimize that, right? You can, we'll talk about actual cases in which it's easy to optimize that, but you're going to assume that each of these sub-problems is actually easy to do, that it's not itself a gradient descent or something like that. You can either find a closed form for it or you can do something nice with it. We'll look at an example in which it's actually easy to do. Each of those steps is a simple closed form minimization or something like that. Yeah.
So if I have only a single function,
Yep.
not decomposing the exponent, I can still use this.
You could by introducing a dummy variable, and we'll see that on the next example. That even if it's technically it looks like it's not really decomposable, you can introduce a dummy variable and it's like it decomposes into two different parts. So yeah, we'll look at the example. It might become a little clearer.
So my question was, does the decomposition come into picture to guarantee convergence? Because if my function is of two variables, a single function is of two variables which is not decomposable, I can still use this and do descent to solve it.
If it's not decomposable, you can still do this. Yeah, the whole point is that it would be simpler to solve those sub-problems. If it decomposes, then hopefully the effect of the one subset of variables doesn't really affect you when you're optimizing the other subset. If they're joint, I don't know, in a too entangled way, then you might not be solving an easier problem when you break the subset, right? So if I just took the lasso as it is and I tried to optimize over x1 first and then x2 and then x3 or something like that, it's not clear that I've made the problem any easier or that it would converge because it's not smooth. So here we'll see that it actually converges. Yeah.
If you have a closed form solution to x1 and x2, I think you will also have a closed form solution
To the original problem? To u. Yeah, the update for u is already in a closed form. I don't have a minimization there, right? The update for x1 t plus 1 I've presently written as an argument problem. We'll see that's easy to do. At least for certain problems that we consider, it'll be easy to do. But the update for u is itself a nice closed form. I didn't mean that the entire optimum for x1 is a closed form. I meant just that this update step for x1 will have a closed form. Yep. Yeah, you just found x1 t plus 1 just before that. And so you use x1 t plus 1 and ut. Why not x1 t? Yeah, it's not symmetric. You're right. It doesn't look symmetric and it isn't. If you were to do it the other way around, you would actually be doing something different. It's not supposed to be symmetric. It's not exchangeable. So if I exchanged it, the update would actually end up being different. You would get a different x2 t plus 1 and a different x1 t plus 1 if you switched those rules. But yeah, it's not intended to be symmetric. Yeah. Yep. Yeah, you can switch the order of x1 and x2. That's fine. As I said, if you choose to do x2 first, then you haven't found x1 t plus 1. So the minimization for x2 will look like L row of x1 t, x2 and ut, and then the minimization for x1, which is afterwards, after you've already found x2 t plus 1, will just be L row of x1, x2 t plus 1 and ut. I mean, you can switch them. I mean, f1, x1 and f2, x2 are switchable, right? I mean, 1 and 2 are really switchable. That's fine. Yep.
If I just fix x1, x2 and differentiate with respect to u, then I won't have the flow term, and what is the frequency of the
I didn't get your question, actually. If you fixed x1 and x2
and differentiate with u,
right, right.
and I won't get that term that contains the flow. Is this in one extent?
No, so if you remember, ut plus 1 was the definition in the definition of subgradient ascent. Okay, so in the definition of subgradient ascent, you had to choose a minimizer. So g of u is the inf over x of L of xu. So if you want to do subgradient ascent in terms of in terms of u, the gradient in terms of u is actually like ax plus minus b, where x plus is a minimizer. So I mean, I have to move in the direction of the gradient. That's the reason that the x plus comes there. I'm not doing a minimization over u. That u step is not a minimization step. It's a gradient step. It's a gradient ascent step, right? So that last. I mean, this update for u is not a minimize over u of fix x1 and x2 and minimize over u. It's a take a gradient ascent because I now know the gradient. The gradient is ax minus b, and now take a step in the direction of that gradient. And that's what the last line is. So it's not that I'm fixing x1 and x2 and taking a derivative. I'm calculating the gradient of g of u because the function I'm trying to optimize is g of u. And the gradient for g of u is x minus b, and I'm taking a direction in that step. Yep. Is anyone? Yeah. Right. Right. Yeah, I don't think it converges. So the question was if I used x1t and x2t in both the updates, that is for the second update I didn't use t plus 1, and then I could parallelize it because I can just do x1 and x2 the minimization for both independently, then does it converge? And I don't think it converges, but if you find a proof that it converges, then maybe you can publish a paper about that. But yeah, okay, so Ryan says yeah, it doesn't, so I think he's tried it. No, he hasn't tried it. No.
The analogy is to do block coordinate descent and do the updates all at once, and that's no, not converge.
Right. So this looks like block coordinate descent, and you know that in block coordinate descent, if you do the updates at once, then it doesn't converge. So.
But just mentioned the trick for that problem is to carve up the problem so that the updates don't interfere with each other. So you can, like, if you want to parallelize something, you try to carve it up in a way so that the update for x2 doesn't matter what the value of x1 is for that step.
Right.
So, for example, if you had a network like a grid graph, right, you could split it so that you do every second column at once, and then the other columns all at the same time, right, or something like that, and you'd be able to parallelize the columns.
Right. Okay. Yeah. Yeah, you can solve it using dual ascent. I mean, you can also solve it using like subgradient methods and stuff. That's fine. This leads to an extremely fast algorithm. You'll see that when you actually implement it, that this algorithm normally converges really fast. It converges under extremely weak conditions, and it's like 3 lines of MATLAB code. So if you actually wrote it, it's literally a for loop over this until you know your residual is really small or something like that, and you'd find that this is just like a really simple code, and it leads to extremely interesting algorithms, which we'll see an example of, where hopefully when you split the variables up, each of these minimizations is actually simple and interesting, and it leads to an extremely non-trivial algorithm which you could not have derived like independently, and that will come up in the example. Actually, let's move on so that we actually see the example. Maybe that will clarify some of the motivation. So just a note on the convergence guarantees of ADMM. There are 2 assumptions which are extremely weak. The one is just that the 2 functions that it decomposes into are just, you know, they're nice. Basically, they're closed, proper, and convex. What that means broadly is that the epigraphs are closed, non-empty, and convex. So that's a very simple assumption about F1 and F2. And the assumption 2 is that the unaugmented Lagrangian, that is, if I used 0 as the penalty parameter, there's no squared term. The unaugmented Lagrangian has a saddle point. Okay, and a saddle point is just a point x1s, x2s, us for saddle. And so the middle term, and if you take any x1 and x2, it's actually larger. So that's the right-hand side. So if I take L0 of x1, x2, but with a fixed us, it's larger than this saddle point. And if I fix x1 and x2s, and I move u, it's actually smaller. So L0 of x1, x2s with u. That's just the definition of a saddle point. And that's actually a very, very weak condition, very reasonable thing to assume. And it's almost always satisfied. In that case, we get 3 kinds of convergence. The residual converges, that is, if you look at the constraint, actually that should be a b, but a1 x1t minus plus a2 x2t minus b goes to 0. Okay, so let me just write that again. So the residual convergence should look like a1 x1 plus a2 x2 minus b goes to 0. Okay. Then the objective converges, and what do I mean by that? If I actually calculate f1 of x1t and f2 of x2t, it actually converges to the optimal f of x star, right? It actually converges to the optimal value. And the dual variables converge to the optimal. So yt converges to y star. So you just note that the primal variables needn't converge. You need more assumptions for x1 and x2 to actually converge to x star. But sometimes you're fine with that because f of x1 plus f1 of x1 plus f2 of x2 converges to the optimal function value. So you know you're sometimes fine with that even if the primal variables don't converge. Those are just the convergence guarantees. They're very, very relaxed assumptions and pretty decent guarantees. Let's look at a nice example for this. This example is titled Generalized Lasso with Repeated Ridge. So what I'm going to show you is that if you had a generalized lasso problem, and you had a nice way to do ridge regression, you could do ridge regression multiple times and solve lasso. Okay, so that's kind of a pretty beautiful result. What's the generalized lasso problem? It's just the first line there. You have ax minus b the whole 2 norm squared plus lambda times you penalize the 1 norm of fx. So why is it called generalized lasso? Is because it like encompasses a lot of problems that are very similar to lasso. For example, if f was the identity, then this is exactly the lasso problem. If a was the identity and f was like a difference matrix, then you get what's called trend filtering. I think Ryan had mentioned that last class. What you get is something like x minus b the whole squared plus norm of fx, and this would just look like the sum of xi plus 1 minus xi. It looks like that, and it's normally used when you have so you have a signal, and the signal has some you want a piecewise kind of constant signal, very few jumps in your signal, and you get noisy observations. So what you want is that xi plus 1 minus xi is sparse in some sense. It's not important, but basically this encompasses a lot of generalizations of the lasso problem, and so that's why it's called generalized lasso, right? So let me actually move that away. So in ADMM form, all I'm going to do is introduce a dummy variable z. Okay, so you can actually see that in our case, the variables don't decompose into parts or anything like that. But I'm going to introduce a dummy variable z for fx. And then what I get is ax minus b the whole 2 norm squared plus lambda 1 norm of z, such that now z is equal to fx, right? Which I'm just writing as fx minus z is equal to 0. So now I have two variables, x and z, which are disconnected. They are related by this linear equality term fx minus z is equal to 0, which is like a1x1 plus a2x2 is equal to b. And so this is of the ADMM form. And it's pretty easy to derive the ADMM updates for this. So we'll see at least what the updates look like. So the update for xt plus 1, you'll note that the right-hand side for xt plus 1 looks like a ridge regression. We'll come to that. But a ridge regression form looks like, I'm going to take A transpose A plus lambda times I, which is like a penalty parameter, the regularization. I invert that and I multiply it by my observations y. Right? So if I just did ridge regression, that's the closed form for it, and this is exactly a ridge regression. The update for z looks like a soft thresholding with some parameter lambda by rho. We'll derive this, but it's just like a soft thresholding operator. And my update for u is just I just add some terms, which is nice. So each of those parts is easy to do if I know how to do ridge, which is really fast and easy to do. You'll note that in the inverse term, it's the same matrix every time. It's A transpose A plus rho F transpose F that I'm taking the inverse of. So I can actually cache the inverse and I don't have to do the inverse at every step. So if you look at the update, it's actually just a matrix vector multiply for xt plus 1, a simple thresholding for z, and an update for u. And I just run this maybe 50 times and I get the solution to a generalized lasso problem, which is pretty cool. So let's just go ahead and derive these updates. It's not too hard. Okay, so that's visible. So let's just, if you look at the update for xt plus 1, it's going to be fix z, fix u, and minimize according to x, right? So if you look at the problem up there, maybe I should just write what the Lagrangian looks like. So it's minimize over x and z of half ax minus b the whole 2 norm squared plus lambda times the 1 norm of z plus, you'll see why I'm doing this soon. I'll explain myself. Rho by 2 times fx minus z the whole squared. Okay. So what I've done is I've added an extra rho there. So that just means that instead of taking my dual variable to be u, I'm taking my dual variable to be rho times u, which is fine. There's no harm throwing in a constant. So if my optimal u was u star, now my optimal u will be u star by rho. So I'm just throwing in a constant just to make the updates look a little nicer. But that's my augmented Lagrangian. And what I want to do is, as I said, if I fix x and z and then fix z and u and look at the update for x, right? So I'm going to just differentiate this with respect to x only. What I'll get is A transpose times axt plus 1 minus b, right? That's the first term. Then I'll get a rho times f transpose u transpose. Oh, sorry, ut. Okay, so that's u at the previous time step. And I'll get a rho times f transpose times f xt plus 1 minus zt, right? That should be equal to 0. So at xt plus 1, I just differentiated it. That should be equal to 0. If you just collect the terms for f, it's basically A transpose A plus rho times f transpose f times xt plus 1, right? That's just equal to A transpose B plus rho times f transpose zt minus ut. Okay, so you should just think of the right hand side as y. Okay, you have some fixed quantity y, A transpose B plus some constant. So this is just some vector y, and all you have to solve is a matrix times x equal to this y, and this is exactly what you get from ridge regression, right? So this is just xt plus 1 being the inverse of A transpose A plus rho times F transpose F, the whole inverse times this y, this observation thing. So that's our update for xt plus 1. It's pretty easy to derive. Now it's exactly the same thing for zt plus 1, right? I'm going to fix xt plus 1 and u and derive the update for zt plus 1. And so what it looks like is essentially deriving with respect to z. I get lambda times s, where s is the subgradient of the one norm, and I get rho times u transpose, ut again, and I'll get a term which is minus rho times fx t plus 1 minus z, right? And that should be equal to 0. That's z t plus 1. So all you get is basically, if you look at the update for zt plus 1, it just looks like fx t plus 1 plus ut minus lambda by rho times s, where this is a subgradient of the one norm. This is essentially the soft thresholding of fx t plus 1 plus ut, right? So if this is the usual soft thresholding for if you have the one norm that you're minimizing. So we get the update for zt plus 1 pretty easily. And now the update for u, now remember it was rho times u, so I get the update for u as just rho times ut plus 1 should be equal to rho times ut, because this was my dual variable, and plus rho times the gradient in some sense, which is fx t plus 1 minus zt plus 1. So then my rho just cancels out, and then I get the update for u. Right, so let me just move that. Right, so the update for u is just a dual ascent step. That's pretty obvious. So it's pretty cool that you wanted to solve a generalized lasso problem, right? Any A, any F, and all you'd had to do was solve ridge regressions, do thresholdings, and add some matrices. Extremely cheap, simple steps. So it's like a 5-line code to solve a generalized lasso problem. I find that very awesome, actually. I'm actually going to just skip over this group lasso part. It's just a pointer that if you had a different kind of penalty up there, which did not look like the one norm of x, but it was a sum of these two norms of x, that's called the group lasso. And then you get the update for z looks like a vector soft thresholding operator, which is slightly different, but I don't think I have time for that. I'll just leave that on. Okay, so let's just take a break for a few minutes. Does anyone have any questions actually about this before we break? So at least this is a very interesting example of why ADMM was useful. It derived a completely new algorithm, it's completely non-obvious that this should work, and it's 5 lines of code, and it works, it converges. And it was in a case where if you looked at the original problem, it would seem like it's not decomposable, and it should seem like you're not really, can't really do much with that. But just writing it in a slightly different form, you can derive nice updates for it and stuff. So you'll actually come across other algorithms in literature that derive cool ADMM updates for them. Yep.
What's the difference?
Like picking the parameter rho is hard. Like we don't really know a good way to pick parameter rho. And I guess another thing is that convergence rates aren't a settled problem yet. So I've told you that it converges. I've not told you the rate at which it converges. And while there are some recent papers in the last 1 or 2 years about it, it's not a settled problem yet. I don't think people completely agree with the proof. Yeah.
It also doesn't converge to brakeman decisions. You compare it to even other thresholding methods. So if you want an answer and you don't care about huge amounts of decisions, you want the process solution, you can get it from my consecutive iteration. But if you want a precise solution, it takes a lot of iterations.
Right. So what Ryan's saying is that if you're happy with an approximate solution and you don't need very high precision, then this will get you that in like 50 iterations or something really quick. But if you want something with very high precision, then it'll take a much longer time to get there. Yeah, it doesn't. Yeah, it's not. Yeah. Okay, let's just take a quick 2-minute break and come back. Okay, so in the second part, I'm going to talk about what's called mirror descent, and for those who've, at least seen the literature of late in the last 1 or 2 years, it's become the most, I guess, popular algorithm, which is now in actually even in reinforcement learning, in online learning, and even in normal gradient methods, mirror descent is something that you'll see a lot of. And I thought it'd be useful to give people an intuition of what mirror descent is doing, because it took me almost a year to understand what it was doing really. And you'll see why it's important also, because in high dimensional problems, up till now we have been talking about how quickly we can optimize something, but we have been talking in terms of number of time steps or number of iterations it takes. But you would also want to know how it scales with dimensionality of the problem. So if I'm solving a problem in n dimensions, how does this scale with n? And you'll see that mirror descent actually scales optimally or near optimally with n, but gradient descent does not. So that's like the motivation for mirror descent, high dimensional problems, getting the right dimension dependence. So for that, we sort of just need to cover some basic definitions, you could say. I'm going to introduce something called brakeman divergence. Okay, so a brakeman divergence, I'm going to call it delta subscript g, so delta g. It's called the brakeman divergence. G is a strongly convex function with respect to some norm. Okay, so I fix a norm over the space I'm working on. It could be the 2 norm, it could be some other norm. So I fix a norm, and G is strongly convex with respect to that norm. So what does that mean? Just recall that strong convexity. So G is strongly convex if G of y is at least G of x plus gradient of G at x transpose y minus x plus some lambda by 2 times y minus x the whole squared. So this is the definition of G being strongly convex. And I mean, there are several equivalent definitions, like if I take the second differential of G, then its Hessian is positive definite with minimum eigenvalue at least lambda. And I'd introduced this in my first review session in the beginning, and we've come across it at times in the course where strongly convex functions lead to good rates and stuff like that. So that's just the definition. And note that the norm there can be any norm. So normally we use the Euclidean norm to define what we mean by a strongly convex function, but if I choose another norm, then I can say that a function is strongly convex with respect to a different norm. That's fine. So if G is strongly convex with respect to a norm, I'm going to define the brakeman divergence, so delta G between x and y, as, if you just read that, that's G of x. So just take G of x, and you have the second term, which is G of y plus gradient of G at y times x minus y. So I'll try to draw that for you, what that's really trying to say. Okay, so you have some function G. So you take a point y, and you move in the direction of its gradient, right? So this is, that point there is G of y. This tangent is like the direction of the gradient, and I move an amount of x minus y. So if that's my point x, right? So then that's G of x, and this point here is G of y plus gradient of G at y transpose x minus y. Okay, so those are the 2 points. One is the value of the function at x, and one is the value if I started at y but I only went in the direction of the gradient, right? So that's like the linear approximation to G. And the difference between these two, okay, so the difference between where is that? The difference between G of x and G of y plus gradient of y transpose x minus y, that difference is what I'm calling the brakeman divergence between x and y. Okay, so that's that difference, right? So for a different G, that delta G of x and y is going to be different. So what is this? You can think of it as it's like a distance measure. So if I asked you what's the distance between x and y, you should always ask, okay, like with respect to what norm, for example. So I'd say, okay, distance between x and y according to 2 norm is x minus y 2 norm squared, or distance between x and y according to the infinity norm is x minus y infinity norm. And so now this is just the distance between x and y according to a function G. So that's what you should think of the brakeman divergence between x and y as. It's just I'm measuring the distance between x and y, but relative to how different they are for a function G, right? So that's what I'm telling you to read it as. If G of x is actually just the 2 norm squared, so if G of x was just 2 norm of x squared, this is strongly convex with respect to the 2 norm, then your delta G of x and y just reduces to x minus y 2 norm squared. Right, so if I chose my function like that, then it's pretty easy to just actually substitute over the x square minus y square plus 2y transpose x minus y. If you just substituted that over there, you'd actually just get x minus y the whole squared. If g was something else, if g was, it looked like, the sum of xi log xi minus xi, this is called the unnormalized entropy, because x log x is like this entropy term, but that minus xi is just in case I'm not on the simplex where it's not a probability distribution, I can still define this function. It's just called the unnormalized entropy, and you can show that it's strongly convex with respect to the one norm, and in that case, the brakeman divergence between x and y, which is just the distance between x and y, but according to some other function, it looks like xi log of xi by yi, and plus some yi minus xi. So that should remind you of KL divergence. So it looks broadly like a KL divergence term. So you have this plus yi minus xi because it's not normalized. That is, I'm not assuming that it sums to 1 or something like that. But so this is just another measure of distance between x and y according to a different function, right? So all we have, this is, so if someone asked you, if you had to think after this class, what is brakeman divergence? It's just the distance between x and y, but measured according to some particular function, strongly convex function that I choose. Yep. Yep. X minus y 1 norm squared, right? So that's what I mean by it's strongly convex with respect to one norm. It means that thing's the 1 norm squared there. Yeah. Okay. Okay. So that's brakeman divergence. It's just like a distance measure. So what are some properties of brakeman divergence? I'm going to assume, of course, that G is, as I said, G is lambda strongly convex. So that's the lambda, how strongly convex it is. And you can just see that by putting y equal to x, I just get 0. Right? So delta G of x comma x just ends up being 0. The last term just, you get G of x minus G of x. And the last term is just x minus x at 0. So it's just 0. So that makes sense, right? The distance between x and x should be 0. That's fine. What do we know by strong convexity? We know by strong convexity that if we just change sides over there, so if we just take g of x plus gradient of x times y minus x, if we take that to the other side, right? So if we just take that to the other side, that's basically the brakeman divergence, which is on the left side. And so the brakeman divergence is at least lambda by 2 times x minus y the whole squared. So it's always positive, right? So it's a distance between x and y. It's always positive. It's at least as large as this x minus y the whole squared. So some nice properties that you think a distance should have. It's kind of easy to see what its derivative is. So if I'm going to take its derivative with respect to x, so just look at the formula up there. Just take the derivative with respect to x. The first term becomes the gradient of x. The second term, which is g of y, disappears. The third term, which is gradient of y transpose x, just becomes gradient of y. And the last term, which is again independent of x, disappears. So we just quite easily see that the gradient of x with respect to x is going to be an important formula. So the gradient of x of this delta g of x comma y, this is just nothing but gradient of g at x minus gradient of g at y. It's just a nice thing to know. It will come up in the algorithm. Again, you can take the second derivative and you'll see it's nice. There's some nice kind of triangle inequality that holds. The distance between x and y plus the distance between y and z. It's not greater than the distance between x and z, but it's the distance between x and z plus some term. So it satisfies some nice kind of properties that might be useful in proofs. But this is just to get a feeling of it's pretty decent as a distance function. It doesn't completely mess up your intuition of what a distance function should be like, right? Okay. So let's just recap gradient descent. Okay, the gradient descent was just I have a set S. I need to minimize x over s of f of x, right? What did I do? What gradient descent was trying to do was the intuition, at least behind gradient descent, was I'm going to minimize a quadratic approximation of f at my point xt. Okay, so basically I have some function that I'm trying to minimize. At any point, I'm going to try and estimate it by a quadratic, and I'm going to try and see where the minimum of that quadratic lies, and I'm going to move in that direction. So you can motivate it by saying that it's nothing but xt plus 1 is nothing but the argmin of x of a quadratic around xt. So it's just f of xt plus the gradient of f at xt times x minus xt plus the Hessian is now just the identity, is just half of x minus xt the whole 2 norm squared. And you can just see, if you just stare at that equation and if you take the gradient with respect to x, you want to find the argmin, you take the gradient with respect to x, what you basically get is the gradient descent update. Right? The first term disappears because it's independent of x. The second term is just the gradient of f at xt. and the last term is just like x minus xt, right? So you just get x is equal to xt plus the gradient times. So of course you'll have a step size there. If you have a step size, that becomes 1 by 2t or whatever your step size is. And but broadly you can think of where do I get this update step for gradient descent from. I'm going to find a quadratic approximation of my function. I'm going to minimize that quadratic approximation, and I'm going to keep doing that, right? So this we discussed this when we had covered gradient descent, if you remember. What do we know for at least for subgradient descent if it's not differentiable? If you remember my problem on homework 2, which moved you through the regret proof, it showed that for projected subgradient descent, what we have is that f of x, that should be f of x capital T. So f of x capital T minus f of x star is at most this term that looks like L2 d2 by root t. So it has a 1 by root t convergence rate. I mean, we proved this. And where L2 was just this maximum subgradient in the 2 norm. So the subgradient of f at x in the 2 norm, that's L2. It's a bound on the subgradient. And d2 is just this diameter term, which looks like the maximum distance between any 2 points in the set is like the diameter. So, I mean, of course, I called it gd by root t in the proof. It's basically, I've just called it here L2 d2 by root t. And this is what we had showed. So if someone's going to ask you, how does this scale with n, right? We have this n-dimensional minimization problem, right? Your set is in n dimensions. And this L2 d2 by root t seems to be hiding the dependence on dimension. But it actually, what you note is this L2 term actually depends on both your function and your set. So your maximum subgradient that you have, of course it depends on your function, but also depends on how large your set is, which dimension it is in. And of course the diameter of your set also is going to scale with n, right? So those terms are kind of hidden. The dependence on n is hidden over there. And we'll see an example later that this dependence on n is not going to be optimal. And so we're going to try and come up with another algorithm for which the dependence is actually optimal. So over here, the idea is basically that gradient descent doesn't use the geometry of the set. So any set S, what it does is I'm going to minimize a quadratic approximation of f and minimize that approximation. It just doesn't take into account the geometry of what the set looks like. It could be a ball, it could be a square, it could be a simplex, it could be anything, and gradient descent is essentially going to do the same thing every time, right? So what we're going to do is do something that hopefully takes into account the geometry of the set. And we're going to see that taking that into account leads to a better scaling of dimension. So I want you to remember the intuition for gradient descent, right? The quadratic approximation, minimize that. What mirror descent does is basically if you're given a norm over your domain S, what it does is it minimizes the quadratic approximation of f at xt, but where the distance is not given by x minus y2 norm squared, the distance is given by the Brakeman divergence between x and xt, right? So it's just the same thing. It's f of xt, the gradient of f of xt times x minus xt, but the last term is no longer that squared norm term. It's this Brakeman divergence between x and xt. And we'll see that, for different sets, a different choice of g makes sense. So if that g was just the 2 norm squared, I would get back gradient descent, because when g is the 2 norm squared, we saw that the Brakeman divergence is just the normal Euclidean distance. So if I chose g to be the 2 norm squared, it's just gradient descent, but I won't always choose it to be 2 norm squared. I'll choose it to be like the unnormalized entropy or some other function, and that'll give us a slightly different update, right? So just to try and see alternatively how the mirror descent update can be written. Okay, I'll just actually go through that calculation. All I've done is, okay, let me throw this paper away. So we have xt plus 1 is argmin over x, right, of what's up on the board. I can throw away the first term because f of xt is independent of x, right? I can just keep the second term, the part that depends on x, so that's just the subgradient of f at xt transpose x. I can again throw away the xt term, which is gradient of f at xt times xt. I can throw away that term, it's independent of x. And that last term, the Brakeman divergence of g between x and xt, I can just expand that out. It's g of x, so that term remains, and minus g of xt, I can throw that away because it's independent of x. So that's minus g of xt, and I don't really care about that. And you have this gradient of g at xt times x minus xt, right? Oh, shift the paper. Right. So transpose x. So this was an x minus xt over here, but I can forget about the xt. So all I've done is I've just expanded the term for the brakeman divergence, and I've just thrown away terms that are independent of x. And what I get is the second line that you can see. It's just argmin of x transpose. You get this one term which is the gradient of f at x. You get this other term which is g of x, and you get this third term which is the gradient of xt transpose x. Okay, so that's what it ends up being. So in many papers, what you'll see is that the update step for mirror descent just looks like this. They're going to tell you xt plus 1 is argmin of this term that looks like x transpose times the difference between two gradients of two different functions f and g, and add this other function g of x, and it'll look like this. And this does not really shed any light on where this update is coming from. Why does it make sense to do x transpose times something plus g of x? But you'll see the update written like this, and you should always think what I'm really doing is minimizing this quadratic approximation of f at xt, where the distance is measured according to brakeman divergence. So that's the first line is what you should really be keeping in mind. But the second line is what you'll see it being written as. Again, you'll see it being written as the third line, which is I'm going to actually take the derivative. It's argmin with respect to x. So let's just differentiate it with respect to x and put it equal to 0. So again, you can just directly see what you'd get over there is the gradient of f at xt minus the gradient of g at xt comes from the first term. The second term just becomes the gradient of f of g at xt plus 1, and I get the second line, right? So I just get gradient of f at xt plus gradient of g at xt plus 1 minus gradient of g at xt is equal to 0. This is just the fact that this is a xt plus 1 is a minimizer of the previous step. So this is kind of an obvious statement. And so sometimes if you just rearrange the terms, what you'd get is you'd see it being written as xt plus 1 is this delta g inverse. So I'll just write that xt plus 1. Maybe I should just write it like this. Delta g of xt plus 1 is equal to delta g of xt minus eta t gradient of f at xt, right? So you know this right hand side, and you can talk about xt plus 1 as being the inverse with respect to this gradient of g term. And so again, another way people talk about gradient descent is they'll draw these two figures for you. They'll call it the primal space and the dual space, and they say you start at a point xt. What you do is you take gradient of g. So what you get over here is gradient of g at xt. Over here you take a step. This step is in the direction of minus eta t gradient of f at xt. So right, so what you get over here is gradient of g at xt minus eta t times gradient of f at xt. And then you take an inverse step. So you take an inverse step, which is gradient of g inverse, and what you get is xt plus 1. Right? So you'll see this kind of a diagram being drawn for mirror descent. I must say that I saw these kind of statements for quite a while, and I had no clue why it was working. Why would you take a step into the dual, take a step in the dual, take an inverse back? At least it didn't tell me why this algorithm was working. And I think that every time you think of mirror descent from now, you'll see it being quoted in these different forms. But what you should really be thinking of in your head is quadratic approximation of f at xt, but I'm not going to use the 2 norm to measure my distance. I'm going to use the brakeman divergence. That's the only difference. Yep.
The eta thing just be multiple g by 1 over
Yeah, sure. Right. So in my as in gradient descent, you can add a step size thing over there, where the brakeman divergence with respect to g you can divide by this step size eta. So that's just the same thing like in gradient descent, you get a step size eta. Right. Like you don't actually take a step size in the gradient, you just multiply it by some. So it's the same intuition. But you should just think of, if you know how to do gradient descent, you know how to do mirror descent. It's doing the same thing, just a different distance measure. That's all it is. Any questions about? Yep. The equation is basically this, right? So this this equation. Do you agree with this, that this xt plus 1 has to satisfy the minimizer? So I just rearranged the term and wrote xt plus 1 as gradient g inverse times that. So all I'm saying is if I start at xt, I first calculate gradient of g at xt, then I take a step, and I take an inverse step. Now this dual is a different dual space. So actually, you'll see that like a primal space consists of your set of points, and your set of gradients lies in what's called a dual functional space. And so you take a step in that different space. So it's normally quoted in, so I'm just telling you this, that because you might see this diagram. This diagram is there in Bartlett's course in Berkeley, and you'll see this kind of statement being, so if you look at Nemirovsky's papers on mirror descent, you'll only see things written of that form, like this arg min of x times that. You'll see things written in that form, and I'm just saying that you'll see it in a different form. You should just, they're not very revealing. When you see that step, you're like, why am I doing something like this? And you should always think about, I'm just doing gradient descent, measuring the distances in a different norm.
And the quadratic approximation comes from like Taylor expansion, right?
Yeah, that kind of, it's not a Taylor expansion really, but that's just a way to justify what gradient descent is doing. You justify it by saying that this is what gradient descent is doing, and I don't always want to measure the distance in the 2 norm squared, and I want to measure it according to some other function. You don't justify it from Taylor expansion. You say, I know what gradient descent is trying to do, and I'm going to try and do something similar but measure distances differently. Yep. Yeah, we'll see. Like, so choosing G is the art in all this. So according to the geometry of the set, you have to choose G appropriately. And so for some kinds of sets, we know how to choose G, but in general, given a very general S, we don't know. But many times we are doing functions in which the set S has a nice geometry, like an L1 ball or something, and then we know how to choose G for those kinds of sets. But it's an art in general. You might choose G badly and do badly. Yeah. Okay, so what are the convergence guarantees for this problem? So we see that now what we have is a general norm, and the gradient of f in the dual norm is actually bounded by this Lipschitz constant. So this L. So I've just subscripted it with an L non to keep telling you that whenever someone says that a function is Lipschitz or the gradient is bounded, you should always ask in which norm. Okay, so that L for different norms is going to be different. So the dual norm of f is bounded. That's equivalent to saying that f of x minus f of y is less than equal to L times x minus y. So if I say that a function is Lipschitz in some norm, it's equivalent to saying that its gradient dual norm is bounded by that constant. I can prove that some other time, but you'll have to take it for me that those two statements are equivalent, saying that the gradient is bounded in dual norm and a function is Lipschitz in the primal norm. Okay, so that's what L is over here. It's the same kind of L as before, just that in gradient descent it was the 2 norm, and so I wrote L2 there. You have a different kind of term for the diameter. So instead of the diameter with respect to the 2 norm, you have the diameter with respect to G. Okay, so you're just going to measure the diameter with respect to this function G, and it has a slightly complicated expression, but it's basically, you can see that what D2 is it looks like I'm going to maximize over x and y of x minus y 2 norm squared, take the square root. So that's what D2 is, which is what we use as a normal diameter. And over here I'm using DG, which looks like the same thing. It's taking a square root 2 times max over y of, now I have this, instead of this x minus y 2 norm squared, I have this brakeman divergence between xg and y, where you can think of xg as being like a center of your circle, like a center of your set. Xg is just a point in your set that minimizes g of x. So it's like a special point. You can think of it like a center. And I'm going to just measure the point y that's furthest away from this center. And you can show that every point x satisfies x minus xg is actually less than equal to this d term. When you define d in that fashion, it really behaves like a radius or a diameter. It's actually, and it looks pretty similar to this d2. And what you get is that f of xt minus f of x star now depends on, instead of L2 d2 by root t, it depends on L in that norm and the diameter, but measured according to g and that norm by root t. So it's a very, very natural looking bound to get. It's an exact generalization of gradient descent to general norms, you could say, and to another function g. This exactly pretty much becomes L2 d2 by root t. If you chose g to be the 2 norm squared, it reduces to the standard setting. And this is basically going to be to the key to everything really. That L norm and dg norm, that's where the dependence on the dimension comes in. And a classic example is the probability simplex and the 1 norm. Okay, so suppose I'm doing minimization over a simplex, like an n-dimensional simplex is just x greater than equal to 0 and 1 transpose x equal to 1. That is the sum of all your points is 1. So it's like the set of probability distributions in n dimensions, right? Discrete probability distributions. That's what we call the n-dimensional probability simplex as. And now assume that your functions are Lipschitz with respect to the 1 norm. And that's equivalent, as I said, to saying that the subgradients are bounded in infinity norm by this constant L1. So this is actually a very weak condition. To say that the subgradients are bounded in infinity norm by L1 is very weak. We earlier used a condition like the subgradients are bounded in the 2 norm. So you'll note that a vector like 1, 1, 1, 1, 1 has a bound of 1 in the infinity norm, but a bound of root n in the L2 norm. It has a bound of n in the L1 norm. So actually, if you say that I want my function to be bounded in infinity norm, that's very weak. You're allowing very large subgradients like 1, 1, 1, 1, 1. It's actually a large subgradient if you measured it in a norm like 2 or 1, but it's still a small subgradient if you measure it in the infinity norm. So the class of functions whose gradient is bounded in the infinity norm is very large. So it's very general, this kind of a statement. So if you were working in something like this, in an n-dimensional simplex, and you wanted to introduce this large class of functions bounded in whose gradient is bounded in the infinity norm, then we would choose g of x to be this unnormalized entropy thing. In this case, the sum of xi is 1, so it just looks like a normalized entropy. And the update ends up looking like what's called exponentiated gradient. That is, the way to update xt plus 1 is not to take a gradient descent step from xt, but is to take like exponential of this step times a gradient. And I can derive it very quickly, but let's just see what we get first. What we get with this kind of an algorithm, you just have to trust me that if you plug this g into the update of mirror descent, then that's the kind of update that you get. It's actually very easy to see. So what you get is that if you try to calculate what is the diameter of the simplex with respect to this function g, with respect to this unnormalized entropy, then the diameter grows like root of 2 log n, right? So if you were to look at your rate, it would look like L1 times root of 2 log n by t, by root t. So basically the rate looks like root of log n by t. That's what your rate looks like. But suppose you used gradient descent on this kind of a space. So you chose g of x to be 2 norm squared and you just got gradient descent. Then you need to ask what is my d2 bound, that is what is my diameter bound in the L2 norm, and it's actually just bounded by a constant which is 1. So my diameter bound over here was root log n, there it's just 1, that's fine. But unfortunately, if you ask what is my Lipschitz bound when I take the 2 norm, it's actually root n times this constant L1. And it's exactly for the reason that I told you, that if I had a subgradient that looked like 1, 1, 1, 1, 1, then its infinity norm is just 1, but its 2 norm of that vector 1, 1, 1 is root n. So if a particular norm is bounded by L1 in infinity, it's actually bounded by root n times L1 when I take the L2 bound. So if you plugged in gradient descent L2 d2 by root t, what you'd get is root n by t is the kind of rate that you'd get. So mirror descent gives you root log n by t, and normal gradient descent gives you root n by t. So that's actually a huge difference when n is large, and it's almost independent of n. Root log n is, you can think of that being independent of n. I'd just like to just quickly show you that you actually get that update. It's actually quite easy to see. You just have to remember that, so since g of x, so let's see, g of x is just the sum over I of xi log xi minus xi. So if I ask what is the gradient of g of x, okay, so if you just differentiate this with respect to xi all you get is log xi. So I'm going to write log x to mean log xi in each of my things. So I'm just differentiating, oops. So I'm just differentiating this with respect to xi. The first term gives you log xi plus 1 minus 1. So you just get log xi. And you do that for each of the xi. So the gradient is just log x, which is like each of those things. And if you remember the mirror descent update, it looked like the gradient of g at xt plus 1 is equal to the gradient of g at xt minus eta t times the gradient of f at xt, right? So what we just get is log of xt plus 1. Oops. So log xt plus 1 is equal to log xt minus eta t times the gradient of f at xt. And so if you just solve for xt plus 1, let's just take exponentiation on both sides. You get xt plus 1 is just xt, and it's the Hadamard. You just have to do this element-wise, really. That's the Hadamard product. Because log of xt was really a vector of log of xi is what I was really doing. So this so this update is very easy to derive. It's just the mirror descent update. Plug in what the gradient is. It's just log x, and you just get the update quite easily. So what we see is that for this kind of a problem, and you'll see that this holds actually for the L1 ball. For problems like the lasso, where you're penalizing the L1 norm, you can actually write them as things like minimize ax minus b the whole squared subject to L1 norm of x less than equal to some constant. Okay, so this is actually kind of equivalent to the lasso, because if I wrote down the Lagrangian form of this, it uses a lambda times norm of x1. So you can show that solving something like this is pretty much like solving something like the lasso. And so this is actually an L. So over here, your set, your constraint set is exactly the L1 ball. It's like the L1 ball of size C. Now, if you're minimizing over the L1 ball, you don't want to use gradient descent, right? Because you're not respecting the geometry. The geometry of the L1 ball is pretty much like the geometry of the simplex. And so you might want to use something else. And so very often you know the geometry of the set. You'll see an infinity ball, L1 ball, sometimes a probability simplex. So if you know the geometry of the set, sometimes you'll be able to pick this function g intelligently. And you can see more examples of mirror descent in the references, Nemirovsky's lecture notes about how you can take other cases where you can actually pick g nicely. Anyway, I think I'm a little bit over, but thanks.